Hello everyone, I'm Henry, and today's me and Anitas would like to present the ALD, which is atomic layer deposition, and this technology is widely be applied in the semiconductor device, so that's the reason why we pick up this device. So first of all, we would like to introduce why ALD and briefly introduce the process of the ALD. And after that, we will just present the analysis of ALDs and its applications in logic, DRAM, interconnect, and emergence memories. So first, why ALD became important? An important thing is that the semiconductor device becomes smaller and more three-dimensional. So the thin depositions will confront a lot of strikers requirements. It include the thermal budgets, became laws and atomic level thickness, and high quality interface, low defect and impurity levels. So LDs answer the scaling problems by controlling growth one surface and reaction at a time, which means LEDs can control very well in nearly nanometers, a few nanometers thickness. When LEDs compared with other thin technologies, for example PVDs and CVDs, so we can see the complete tables as below the LEDs the have the growth behaviors, the sequential limit, self-limit service reactions is the service reactions only in the molecular levels. So the strength will be apparently have the atomic scales, thickness controls, and conformities. But the weakness, the limitations is the slower growth per cycle times. So it should be have apply into the high volumes device. For example, the semiconductor conductors nanostructures is chosen, ALD is chosen as convergence, and atomic scales control matters more than row deposition speed. And the core ALD process is we have the precursors, the reactants, and when the precursors has been introduced into the chambers, the vacuum chambers, and it will have some chemical absorbs into the substrate surface, and we purge some gas on the surface, and the purged gas will remove the byproducts or excesses precursors. So after that, we introduce the co-reactant B and plus into the chamber, so there will be some chemical reactions between the reactant the precursor A and reactant co-reactant B. And after that, we still introduce some project gas to remove the byproducts. So that is one cycle. So we will becomes um, many circles to until the thickness has been achieved we decide. And one circle is only deposition about zero point 0.5 to 2 points Armstrongs depend on the materials system. And obviously, precursors is quite crucial in ALD. And as you can see, no ideal chemistry cause delays, nucleations, impurity, issues, or non-conform so non-conform step coverage. So others common co-reactants including um, waters or H2 plasmas or O3, O2 plasmas can also use as the co-reactants. And process windows is quite crucial in obvious in all things vacuum technologies. So LED windows is limited by the temperatures, the pressures, the process times. For example, in in temperatures, when the temperature is too low, there was some condensation in compressed reactions. And when the temperatures became too high, the precursor will obviously decompose it. So the windows is to maintain the stable range. And we are going to take examples about the action LED for high case dielectrics. The precursor can be chosen in TMAs and HFCl4s precursors, and those things are important in semiconductors, so you can achieve some high case dielectrics. For example, the L2s, O3s, the HFO2s are very important to in semiconductors. So when the service reaction happens, the ligand exchange and hydrogen transfers apparently happens in this stage. And after that, we introduce some co-reactants, including waters or O3 or O2 plasmas, and also after that the high K things, including those oxidize will deposits on the surface, of course in a few nanometers. So that's my introduction, and I would like to hand the remaining slides to Anin Natida. Thank you.